The telegraphist aboard HMS Vanquisher pressed his headset tighter against his ear, straining to hear anything beyond the howl of wind tearing through the destroyer's superstructure. Outside, waves the height of a 4-story building marched across the Denmark Strait in endless procession, their crests torn into horizontal spray by 70-knot winds that turned seawater into ice the moment it touched steel. The temperature gauge read -12 Celsius. The barometer was still falling. 200 miles south, 3 German destroyers had already abandoned their patrol. Z-29, Z-33, and Z-38, each displacing over 2,400 tons, built in the finest shipyards of the Reich, crewed by men every bit as brave as their British counterparts, were at that moment running hard for the shelter of Norwegian fjords. Their captains had filed reports using identical phrases: weather conditions prohibitive for continued operations, sea state dangerous to hull integrity, unable to maintain station. Yet here was Vanquisher, a V-class destroyer that weighed barely 1,800 tons, not merely surviving these conditions, but actively hunting. The ASDIC operator had something on his screen, a contact, possibly metallic, possibly moving, in seas that should have rendered sonar utterly useless, in conditions that German naval doctrine had classified as survival weather only. A British destroyer was preparing to attack. This wasn't an isolated incident. This was the pattern. Month after month, through 3 winters of Atlantic warfare, British destroyers maintained combat operations in weather that sent larger, supposedly superior German vessels fleeing for port. The disparity wasn't courage. Both navies bred hard men who didn't break easily. This was engineering defeating engineering, design philosophy overcoming displacement figures. Decades of institutional knowledge about the North Atlantic forged into steel and rivets. The paradox deepens when you examine what these ships actually were. German-type 1936A destroyers looked formidable on paper. They stood taller out of the water. They mounted heavier armament. They could make 38 knots in trials. Their design incorporated cutting-edge thinking about hydrodynamics and stress calculations. They should have dominated their smaller British opponents in every measurable category. Instead, the Kriegsmarine's patrol reports from that winter tell a story of mounting frustration. Operation aborted due to weather, forced return to base, hull damage sustained in heavy seas, unable to maintain pursuit. The admirals in Berlin watched their destroyers, which cost more to build and looked more impressive in fleet reviews, repeatedly fail to operate in conditions where the Royal Navy simply continued working. What HMS Vanquisher's crew didn't know that February night, as they pursued their ASDIC contact through a Force 9 gale, was that they were demonstrating the result of choices made decades earlier. Choices that had nothing to do with wartime urgency and everything to do with geographic reality. Britain was an island that lived or died by Atlantic convoys. Germany was a continental power that had designed its fleet for Baltic and North Sea operations. When war came, both navies found themselves tested by waters only one of them had truly planned for. The story of why smaller British ships could hunt submarines through storms that defeated larger German vessels isn't really about ships at all. It's about what happens when engineering meets the North Atlantic, that stretch of grey water between Newfoundland and Ireland where waves build across 2,000 miles of open ocean, where winter storms generate swells with periods exceeding 15 seconds, where the sea doesn't care about your displacement tonnage or your theoretical maximum speed. The Atlantic tests every design assumption, and by 1943, those tests were producing clear results. Stand on the deck of HMS Hesperus in Liverpool docks if you could travel back to 1942 and look at where her bow meets the waterline. You'd notice something that seems almost wrong at first glance. The hull doesn't cut down vertically into the water like you might expect. Instead, the forefoot extends deep beneath the surface, while the upper bow flares outward in a pronounced curve. This combination represents the Royal Navy's solution to a problem that had cost lives throughout the First World War. How do you prevent a light, fast ship from being thrown backwards or buried when it slams into a wave taller than the bridge? The flared bow works through deflection rather than confrontation. When an Atlantic roller hits a vertical bow, basic physics applies. The water has nowhere to go but up and over, burying the foredeck under tons of green water. That weight forward pushes the bow down, which can lead to pitch poling, the ship somersaulting end over end, or at minimum, damage to forward equipment and injury to crew. British designers, learning from disasters in the previous war, angled the upper bow outward at roughly 30 to 40 degrees from vertical. When a wave strikes this flared section, the geometry forces water to split outward and away from the ship rather than climbing aboard. The destroyer still takes spray, certainly, but the bulk of each wave's energy gets redirected sideways, where it can't destabilize the vessel. The deep forefoot serves a complementary function. This extended underwater section, sometimes reaching 2 meters below the nominal waterline, acts as a cutting edge that penetrates the wave before the main hull arrives. HMS Jervis, a J-class destroyer launched in 1938, had a forefoot that extended 1.8 meters below her loaded waterline. When Jervis met a 12-meter swell, that forefoot sliced into the wave's lower portion, whilst the flared bow above handled the crest. The ship effectively split each wave into manageable components rather than taking the full force as a single impact. This allowed destroyers to maintain 18 to 20 knots through seas that would force a bluff-bowed vessel to reduce to bare steerage way. Compare this to German-type 1936A hull forms. These destroyers featured more vertical bows with less pronounced flare, a design that worked admirably in Baltic conditions where waves are steeper but shorter. The shallower forefoot, whilst reducing drag in calm water and contributing to those impressive trial speeds, provided less bite in long Atlantic swells. When Z31 encountered heavy weather during operations off Norway in January 1943, her log recorded repeated incidents of the bow lifting clear of the water entirely, the propellers racing as they lost grip, violent slamming when the hull crashed back down. The ship remained seaworthy, but combat operations became impossible. Gunnery directors couldn't maintain target solutions. The crew exhausted themselves simply holding on. British destroyers had learned to manage this motion through decades of iteration. The Tribal class of 1938 featured particularly aggressive bow flare combined with a forefoot that extended 2 full meters below the waterline. During trials off the Hebrides in February 1939, HMS Cossack maintained 22 knots through force 9 conditions, wind gusting to 47 knots, waves exceeding 10 meters. The captain's report noted heavy weather working, but ship remains under full control, with no reduction in combat capability. That phrase, combat capability, marked the critical distinction. Any properly built destroyer could survive a storm by heaving to and riding it out. British destroyers could hunt through it. The Hunt-class escort destroyers took this philosophy to its logical conclusion. They sat low, almost menacingly close to the waterline, with freeboard amidships of just 3.2 meters, compared to 4.1 meters on German-type 1936 destroyers. They looked like they'd be swamped by the first serious wave. Naval observers from neutral nations who inspected HMS Brecon in 1941 expressed surprise that the Royal Navy considered such a wet deck design suitable for ocean escort work. Then those observers saw Brecon operating in a Force 8 gale off Iceland, and the comments stopped. The ship that looked vulnerable proved nearly unshakable. Lower freeboard creates a lower center of gravity. Basic physics, but the implications run deep. Every ton of steel positioned high in a ship raises the center of mass. The further that center sits above the waterline, the more leverage wind and waves have to heel the vessel over. German destroyers, with their tall hulls and substantial upperworks, presented considerable windage in a 40-knot beam wind. Z-29 could heel 12 to 15 degrees simply from wind pressure against her hull and superstructure before a single wave struck. British Vi-class destroyers in identical conditions heeled perhaps 6 to 8 degrees. That difference meant British crews could still service depth charge racks and operate weapons whilst German crews were clinging to stanchions. The metacentric height, the measure of initial stability, favoured the lower, beamier British designs. HMS Opportune, an O-class destroyer with 10.7-metre beam and 3.4-metre freeboard, had a metacentric height of 1.1 metres. This relatively modest figure meant she rolled more gently in moderate seas, which sounds like a disadvantage until you understand the alternative. German destroyers, with their higher centres of gravity and taller hulls, had lower metacentric heights, sometimes below 0.9 metres, which produced violent, snappy rolling in storm conditions. This sharp rolling motion exceeded the ability of fire control systems to compensate. British destroyers rolled more certainly, but they rolled predictably and relatively slowly, allowing gun crews to time their firing and ASDIC operators to maintain contact through the roll cycle. The reduced windage paid dividends in survival scenarios. On the 26th of December 1942, HMS Achates found herself caught in a North Atlantic winter storm with winds exceeding 60 knots. The captain's report described green water sweeping the entire foredeck, but the ship maintained steerage way and answered helm throughout. The low profile meant wind couldn't get underneath and lever the bow sideways. German destroyer Z-27, caught in similar conditions off Norway 3 weeks earlier, reported her bow being blown 20 degrees off heading despite full rudder correction. The taller hull caught wind like a sail, and in mountainous seas, that loss of directional control could drive a ship beam-on to the waves, a potentially fatal orientation. British designers accepted trade-offs knowingly. Lower freeboard meant wetter decks in any weather. Crews worked constantly drenched. Seawater invaded spaces that stayed dry on German ships. Equipment suffered from salt corrosion more severely. Living conditions were frankly miserable. V-class destroyers earned the nickname very wets for good reason. But wet and operational beats dry and harbour-bound. When Admiral Dönitz reviewed U-boat loss statistics in early 1943, he noted with frustration that British escorts maintained effectiveness in weather conditions his own intelligence staff had classified as prohibiting surface operations. The engineering failure that doomed German destroyer operations in the Atlantic started in the boiler rooms. Kriegsmarine destroyers mounted high-pressure Wagner boilers operating at 70 kilograms per square centimetre, cutting-edge technology that delivered impressive power-to-weight ratios in calm water. These superheated systems produced steam at 450 degrees Celsius, enabling the turbines to generate 70,000 shaft horsepower and push 2,400-ton hulls to 38 knots during trials. The problem emerged when those same ships encountered sustained heavy weather. Violent motion disrupted water circulation in the boiler tubes, creating hot spots that could cause tube failure. Once tubes started failing, the entire propulsion plant had to be shut down to prevent catastrophic boiler explosions. Z-20 Carl Galster experienced this failure mode on the 8th of March 1942 whilst operating northeast of Iceland. 6 hours into a Force 9 gale, engineering reported loss of steam pressure in the forward boiler room. Inspection revealed 3 ruptured tubes. The ship had to reduce speed to 8 knots on one boiler, insufficient to maintain heading in heavy seas. Z-20 spent 11 hours wallowing beam-on to 10-metre waves before conditions moderated enough for her to limp back to Trondheim. British destroyers used lower-pressure Admiralty 3-drum boilers operating at 21 kilograms per square centimetre. Less efficient on paper, certainly, but far more tolerant of the motion and vibration that Atlantic storms inflicted on machinery. The lower operating pressures and temperatures meant tube failures rarely escalated to catastrophic casualties. A British destroyer might lose some power output in heavy weather, but she rarely lost all propulsion. Structural integrity posed equally serious problems. German destroyers employed longitudinal framing for most of their hull length, a weight-saving technique that worked brilliantly for ships operating in sheltered waters. But longitudinal frames concentrate stress along continuous members rather than distributing loads across transverse ribs. When a destroyer's bow slams into a wave, the impact generates torsional stress that twists the entire hull. Transverse framing, used throughout British destroyer construction, spread these torsional loads across multiple frames. Longitudinal framing channeled them along fewer, more vulnerable structural paths. The consequences appeared in damaged ships returning to German ports throughout 1942 and 1943. Z-25 suffered hull cracking near frame 38 after a North Sea patrol, cracks that propagated along longitudinal stringers. Z-31 developed stress fractures in her keel structure after repeated operations off Norway. Repairs became increasingly complex as dockyard workers discovered cracks had propagated further than initially assessed. By contrast, British destroyers certainly suffered weather damage, but catastrophic structural failures remained rare. The robust transverse framing system, whilst heavier, proved more forgiving of the punishment Atlantic operations delivered. Top weight compounded every problem. German designers mounted 5 12.7-centimeter guns to match the firepower of light cruisers, an admirable goal that placed significant mass high in the ship. The forward superfiring turret sat 6.5 meters above the waterline. The twin torpedo tube mounting added another 8 tons amidships at deck level. Fire control directors perched even higher. All this weight above the center of gravity reduced stability margins and increased rolling violence. When Z-29 encountered heavy weather during Operation Front Theatre in September 1943, she rolled through 42-degree arcs, motion so violent that unsecured equipment broke loose and several crew members suffered injuries. Ships rolling that severely can't fight effectively even if machinery remains functional. British destroyers carried lighter armament positioned lower, 4 4.7-inch guns instead of 5 5-inch weapons, and those mountings sat closer to the deck. The sacrifice in broadside weight, roughly 27 kilograms per salvo compared to 35 kilograms for German destroyers, bought precious stability that translated into operational capability when seas turned nasty. But the real story, the one that determined which navy could hunt submarines through winter gales, wasn't just about individual design choices. It was about why those choices were made in the first place. The Kriegsmarine's destroyer program emerged from unique constraints that shaped every rivet and frame. After Versailles, Germany couldn't build capital ships until the mid-1930s, so destroyer design accelerated ahead of broader naval strategy. When Admiral Raeder's staff drafted specifications for the Type 1934 class in 1933, they envisioned fleet destroyers supporting battleship operations in the North Sea and Baltic, waters where wave periods average 5 to 7 seconds and fetch distances rarely exceed 300 nautical miles. These are choppy seas, certainly, but fundamentally different from Atlantic swells that build across 2,000 miles of open ocean with wave periods stretching to 15 seconds. German designers prioritize speed and hitting power for short, sharp engagements in relatively sheltered waters. They were preparing for the wrong war, not through incompetence, but because geography and treaty restrictions had shaped their assumptions. The Kriegsmarine expected to fight in the Baltic and North Sea. They built ships accordingly. The Royal Navy had been designing destroyers for Atlantic operations since the type emerged in the 1890s. Every iteration learned from predecessor failures. The River-class destroyers of 1903 proved too lightly built for North Atlantic patrols. Several broke their backs in heavy weather. The Tribal class of 1907 sat too high and rolled dangerously. By the time the V and W classes entered service in 1917-18, British naval architects had accumulated painful wisdom. Destroyers operating west of Ireland needed hulls that worked with ocean swells rather than trying to ride above them. This knowledge crystallized in the interwar years when the Admiralty drafted requirements for the A-class destroyers in 1927. Specifications explicitly stated these ships must maintain combat effectiveness in Force 8 conditions, winds of 34 to 40 knots with wave heights reaching 25 feet. Not survive, mind you, but fight. That requirement shaped everything. The subsequent B, C, D, E, F, G, H, and I classes that followed through the 1930s refined this Atlantic-capable template. Each class incorporated lessons from winter exercises off Scapa Flow, where destroyer flotillas deliberately operated in foul weather to identify design weaknesses before war rendered such knowledge costly. Geography determined destiny. Britain's survival depended on Atlantic convoys, so British destroyers evolved to hunt submarines in the worst conditions that ocean could produce. Germany's strategic calculus centered on Baltic security and North Sea dominance, at least until Hitler's ambitions outpaced the Kriegsmarine's building program. When war came in 1939, the German Navy discovered it was fighting in waters its ships weren't truly designed for. The institutional culture differed as well. Royal Navy destroyer captains earned their commands through years of North Atlantic experience. They'd served as junior officers on patrol in the western approaches, weathered February gales off the Hebrides, learned which sea states permitted ASDIC operations and which didn't. This knowledge fed back to the designers at Bath and Barrow. Kriegsmarine destroyer commanders, by contrast, trained in the Baltic, where winter meant ice, not mountainous swells. Their feedback to German shipyards reflected different operational realities. Neither navy was wrong within its original context. Both made rational choices based on expected operating environments. But the North Atlantic doesn't negotiate. It tests every design assumption, and by 1941, those tests were failing one navy whilst validating the other. Return to HMS Vanquisher on that February night in 1943. The ASDIC trace had firmed up. Metallic return, moving at 6 knots, depth 40 meters. U-boat attempting to position ahead of convoy JW-55B using the storm as cover. Because no surface ship should be able to maintain sonar contact in Force 10 conditions. But British destroyers wrote their own rules about what should be possible. At 0847 hours, Vanquisher rolled a pattern of 5 depth charges set to 150 and 250 feet. The explosions were barely visible through spray and snow, but the ASDIC operator reported the contact breaking up. Metal-on-metal sounds that meant hull plates separating under pressure. U-601 did not survive. Of her crew of 46, none saw home again. Vanquisher's log entry remains characteristically understated. Prosecuted contact to destruction, weather conditions heavy, resumed station 0935 hours. There's no mention of the extraordinary seamanship required to maintain accurate depth charge attacks whilst the ship pitched through 30-degree arcs, or the fact that German surface forces had already admitted defeat against the same weather. The convoy, JW-55B, 39 merchant ships carrying tanks, aircraft and ammunition to Murmansk, had sailed from Loch Ewe on the 20th of December into weather that even Arctic veterans called exceptional. By Boxing Day, sustained winds reached 50 knots with gusts touching 70. Wave heights exceeded 15 meters. Air temperature held at -8 Celsius, whilst spray froze instantly on any exposed surface. This was the Arctic Ocean asserting dominance, and somewhere beneath those grey mountains of water, German submarines were hunting. The German destroyers assigned to shadow JW-55B had already withdrawn. Z-29, Z-33 and Z-38 received orders on Christmas Day to intercept the convoy, but by dawn on the 26th, all three reported weather damage forcing return to Altenfjord. Z-33's log recorded a fracture in her forward hull plating after repeated pounding. Z-29 lost her forward rangefinder when a wave tore it clean off its mounting. These were not poorly built ships. They'd been constructed to rigorous standards at Germania and Deschimag yards. They simply couldn't operate in conditions that the Atlantic and Arctic Oceans produced with routine malice. HMS Obdurate prosecuted her contact through waves that buried her foredeck under 3 meters of water every 90 seconds. Ice accumulated on her forward gun, mounting at roughly 30 kilograms per hour. Ratings armed with wooden mallets worked in rotating shifts, smashing ice off equipment before the weight could destabilize the ship. The Azdic dome mounted beneath the hull somehow continued functioning despite seas that should have rendered sonar contact impossible. HMS Matchless and HMS Musketeer, sister destroyers in the screen, engaged 2 more U-boats that day. Matchless forced U-7 or 16 to dive in conditions where the submarine couldn't safely surface again. Her commander eventually had to risk it anyway, and British gunfire finished the job. The engagement reports from all 3 British destroyers note heavy weather, but never suggest it prevented operations. Meanwhile, Kriegsmarine war diaries from the same date record destroyer force abandonment of patrol due to prohibitive sea conditions. The contrast wasn't lost on German naval intelligence. A captured Kriegsmarine analysis document from February 1944 specifically noted British destroyers' inexplicable capability to maintain combat effectiveness in weather exceeding acceptable operational parameters. The analyst couldn't grasp that those parameters had been written for different ships operating in different seas. The mid-Atlantic gap measured roughly 600 nautical miles across at its widest point in 1942, that deadly stretch of ocean beyond the range of land-based aircraft where convoys sailed without air cover. U-boat commanders called it the Black Pit and hunted there with near impunity through the first half of 1942. Wolfpack tactics worked because submarines could shadow convoys on the surface, call in reinforcements, coordinate attacks. The only defense was surface escorts, and those escorts had to remain operational regardless of weather. By autumn 1943, British destroyers' all-weather capability had turned the Black Pit into a graveyard for U-boats. The numbers tell the story. In November 1942, convoys crossing the North Atlantic lost an average of 4.2 merchant ships per convoy to U-boat attack. By November 1943, that figure had dropped to 0.6 ships per convoy. What changed? Long-range B-24 Liberators finally closed the air gap in spring 1943, certainly. But equally critical was the Royal Navy's ability to maintain continuous surface escort regardless of weather. German naval analyses from this period repeatedly cite persistent British destroyer presence during heavy weather as a factor degrading Wolfpack effectiveness. U-boat commanders couldn't exploit storms as cover anymore because British escorts continued prosecuting contacts when German surface units had withdrawn. The tactical calculus shifted fundamentally. Prior to 1943, a U-boat caught on the surface in a Force 8 gale had reasonable odds of escaping. Pursuing destroyers would struggle to maintain speed and sonar contact. By mid-1943, those odds had collapsed. HMS Hesperus demonstrated this on the 11th of May 1943 when she ran down U-223 through a Force 9 gale south of Iceland. The submarine attempted to dive, but Hesperus held Azdic contact through wave heights exceeding 12 meters and delivered a depth charge pattern that crushed U-223's pressure hull. Her commander, Captain Lieutenant Peter Gerlach, had previously escaped British destroyers twice by using heavy weather as cover. That tactic no longer worked. Donitz's daily U-boat situation reports from late 1943 reveal mounting frustration. Entry after entry notes contacts broken off due to heavy weather preventing surface operations. But those same reports acknowledge British escorts maintained pressure regardless of conditions. On the 17th of December 1943, Dönitz wrote to Raeder that the enemy's apparent immunity to weather conditions we find prohibitive has severely degraded Wolfpack coordination. Surface reconnaissance by our destroyers cannot be maintained in Atlantic winter conditions. He was describing a capability gap that technology alone couldn't bridge. This was institutional knowledge embedded in hull forms developed over decades. The operational tempo told its own story. Between January and May 1943, Royal Navy destroyers in Western Approaches Command logged an average of 24.3 days at sea per month. Kriegsmarine destroyers operating from Norwegian bases averaged 11.7 days at sea during the same period. Weather accounted for much of that discrepancy. British ships sailed and fought through conditions that kept German destroyers in port. Every day a German destroyer spent weatherbound was a day U-boats lacked surface support and convoy tracking. The Wolfpack tactic required coordination. Submarines spreading across patrol lines, one making contact, others converging for mass attack. This required predictable surface conditions and reliable communication. Atlantic storms disrupted both. German destroyers that might have provided weather reconnaissance and radio relay sat in fjords waiting for calmer seas. British destroyers remained on station, forcing U-boats to submerge defensively and lose contact with convoys they'd been shadowing. By the time weather cleared, the convoy had gained 200 miles and changed course. May 1943 became known as Black May in the U-boat service. 41 submarines lost in 31 days. The turning point in the Battle of the Atlantic came from multiple factors, certainly. Improved radar, more escort carriers, better intelligence from Bletchley Park, increased numbers of escorts. But underpinning all these advantages was the simple fact that British destroyers could remain on station and fight in conditions that rendered German surface forces ineffective. Naval architecture is rarely celebrated in histories of the Second World War. We remember the codebreakers at Bletchley Park, the corvette captains who shepherded convoys through submarine-infested waters, the air crew who flew exhausting patrols over grey seas, but the engineers who specified hull flare angles and metacentric heights in the 1920s and 1930s shaped the Atlantic battle as surely as any admiral. Their decisions, often made in peacetime design offices without any certainty that war would come, determined which navy could fight when the North Atlantic turned savage. The British advantage wasn't technological superiority in the conventional sense. German engineers understood hydrodynamics and metallurgy as well as anyone. Wagner boilers represented advanced thinking. German fire control systems often outperformed British equivalents in testing. The difference lay in design philosophy rooted in operational experience. The Royal Navy had spent centuries learning that Atlantic weather was as much an enemy as any opposing fleet. That knowledge accumulated through disasters, ships lost in storms, designs that failed in service, bitter lessons purchased with sailors' lives. By 1939, those lessons were encoded in hull forms, stability calculations, and equipment placement that prioritized fighting capability over almost everything else. German naval design evolved under different pressures: Versailles restrictions, Baltic geography, and continental strategic thinking produced ships optimized for a different war in enclosed seas. When Hitler's ambitions pushed the Kriegsmarine into Atlantic operations, those ships faced conditions their designers hadn't prioritized. The result wasn't German naval incompetence. Z-class destroyers performed admirably in the Baltic and North Sea, where they'd been designed to operate. The North Atlantic simply demanded different compromises, and by the time that became apparent, German yards were committed to designs already in production. The human cost of these engineering choices played out in frozen convoy battles and submarine warfare statistics. Every British destroyer that remained operational through a winter storm was a destroyer that could prevent a merchant ship sinking, could rescue survivors from torpedoed vessels, could force a U-boat to dive before it achieved firing position. German destroyers that turned back in heavy weather weren't failing their duty. Their ships simply couldn't maintain combat effectiveness in conditions that British destroyers handled routinely. The sailors aboard Z-29 or Z-3 were no less brave than those aboard HMS Obdurate or HMS Hesperus. Their ships had been built to answer different questions. By 1944, the Atlantic's verdict was clear. U-boat losses exceeded replacement rates. Convoy losses had dropped to levels that no longer threatened Britain's survival. The Kriegsmarine had effectively conceded surface control of the North Atlantic. Weather capability contributed significantly to this outcome. British destroyers wrote the standard for what operational in all weather actually meant. Not survival, but sustained combat effectiveness through conditions that would keep most navies in port. Modern naval architects still study these destroyers when designing vessels for high-latitude operations. The flared bow has become standard on ships intended for polar service. The lessons about center of gravity, freeboard and hull, form resonance remain relevant. Perhaps most importantly, the recognition that ships must be designed for their actual operating environment, not the environment engineers wish they faced, echoes through every maritime design office. The North Atlantic taught that lesson in steel and salt water. The destroyers that learned it best were the ones that could hunt submarines through storms that forced everyone else to seek shelter. On that February night in 1943, as HMS Vanquisher resumed her station in convoy JW-55B's screen, her crew didn't think about hull forms or metacentric heights. They thought about hot tea when they came off watch, about getting the ice cleared before it built up too much, about staying sharp for the next ASDIC contact. They were doing their job in conditions that had sent larger ships running for port, and they did it because 40 years of hard-won knowledge had been built into the very bones of their ship. That knowledge, encoded in flared bows and deep forefoots and low centers of gravity, kept convoys moving when U-boats expected storms to provide cover. It kept escorts on station when wolfpack tactics depended on surface raiders withdrawing. It meant British destroyers could hunt when German destroyers had to hide. In the end, that made all the difference. The Battle of the Atlantic wasn't won by any single factor, but it couldn't have been won without ships that could fight in the weather that ocean produced, and those ships existed because the Royal Navy had spent decades learning what the North Atlantic demanded, then building vessels that could deliver it.